Hi everyone. So in this video we want to create a peel off effect. So something like, burnt off skin that flies away, or something like something breaks through an egg or something like that. There are different flavors of this effect. But what we want to use is this head, and this is actually the head of Tommy. So here's Tommy, and I use a clip to cut off his head, and then I use a match size to make the head stay on the ground in the center by putting justify Y to min. And then I have a lot of holes here from the clip, and I use a polyfill to make him watertight. And then we use our good old VDB from polygons trick to convert it to a VDB and then back to a polygon, so that we have one object that is watertight. And then, because I recorded this before actually, I now decided to record it again with a bigger scale. So I scaled his head up by 5. So it's not the actual real scale of the head. And the reason is that I noticed that Vellum becomes a bit more stable and easier to control when we work on a scale that is roughly a meter. You will be able to use all the techniques I show here with an actual sized head as well, but it makes it a bit easier and more streamlined to show it a little bit bigger. And for something like this, I think the scale is not super important. Okay, on the object level, I have an environment light so that Tommy looks a bit nicer. And let's go into our geometry here. I prepared for this so that we can create the simulation. So what we want to start with is we want to fracture this. And since this will be a membrane, and this is a Vellum simulation, so it will behave like cloth, let's use an edge fracture, of course. And currently you don't see anything because we have to activate the visualization, and here you can see that it creates pieces. So let's increase them because we need way more. Let's say maybe 200. Yeah, that's not too bad. And then of course we need a cloth constraint, and this goes into our Vellum solver. I can use J here to connect all the connections quicker. And let's start this and see what happens. So everything falls down, which is good. So let's stop it from doing that, because of course this is supposed to be skin around the head. So let's take the head we already have and take this as a collision object and see what happens. And we see the guide geometry. So the easiest and quickest way of getting rid of this is creating a null that we look through. And what you can see is that it still falls down as if there was no collision object. And this is something you have to be careful with when you use the same geometry for the cloth source and the collision. This is currently on top of each other. So this is why the collision doesn't work. What we should do here is we should kind of fatten up the skin geometry a little bit, and we can use a peak for that. So with a peak, we basically make the whole geometry move outwards towards the normals. And you can see when you increase that, then our head becomes a bit too big. So let's make something more reasonable, maybe something like this. And what's important here is that the thickness should match with the thickness that we use in our cloth. If we look through our Vellum cloth and we visualize the thickness, we can see that this is the thickness that will be later used for the collision. So let's compare that with the geometry we are actually using, which is the gray one. And you can see now there's a pretty big gap. So let's lower this maybe to something like this. Now the gap is closer. We can actually go even smaller than that. And I think that's about right. So as you can see here, the gray one is the geometry underneath. So this one. And on top of this is our cloth. Now, of course, you could have also shrunk the geometry here, but I just fattened the skin. Doesn't matter, one of the two. And if I run this now, we should see that the collision now works. And you can see everything falls down, but in the few kind of stay on top of the head, of course, which makes sense. Cool. So we don't want it to fall apart like this though. So we have to kind of sew them together. And for this, of course, we use the weld constraint. And when we look through it, we can see that it finds all the connections. So that's promising. So let's run the simulation again. And that looks good. It's just that the skin, because of course it's cloth right now, is way too soft. So let's go into our constraints and let's make sure we increase the stretch stiffness. Let's do something aggressive, like 1000, and see what happens. And it's still pretty soft. And the reason, of course, is that we have a huge amount of geometry here. So if we look through this and show the points, this is really dense geometry. We're talking about 50,000 points. Now you can do it with that, but what you will end up with is a super high substep number. So let's try 10 and hopefully we should see a better result. But of course the whole simulation will be very slow. And you can see it's better, but very slow. So an alternative to that, even though that would be the right approach, is in our case, we don't need that much geometry. This is just something that came out of our VDB convert. So let's just make sure that we remesh the whole thing to something that is as low as possible. So maybe 0.005, that's not too bad, but maybe this one is, yeah, this is pretty good. And we end up with only 6,000 points. Actually, I think we can afford a bit more. Yeah. So we go from 50,000 to 10,000. I think that's all right. Let's lower the sub steps again and see what comes out of this. Okay, so this is still too soft. Let's try sub steps of 2. Getting better. Maybe sub steps of 4. Yeah, I think that's good enough for us. So everything stays together now. But of course, that's not what we want. We want it to break apart. So what we can do now to break this apart is actually, we can do multiple things. For example, we could break the Vellum constraint. And one way of doing this is using the built-in breaking threshold. But in my experience, it doesn't work very well because you need some strong force that breaks it. And that doesn't really look like peeling off. We will use the weld nonetheless because it will look more natural later on, but we will actually for now disable it because we want to activate the pieces in a more efficient way by just starting them deactivated and then activate them based on a controller. So this is exactly how we learned it, for example, in pop grains, and we will use it the same way here. Now we have to figure out how to stop a geometry in Vellum. And this is actually something you can find when you Google for Vellum attributes, because then you will find the help. And here there's a lot of very interesting stuff to learn, a lot of attributes you can use to override certain Vellum properties. And then you will find the attribute stopped. And as you know, this is the attribute we also use in pop grains. Now in Vellum, it's a bit more complex than that. We can actually control not only kind of on and off, we can also control if it's still allowed to change the rotation or just the translation, or we can stop both. So this is pretty interesting. And by the way, there is a good website I can recommend from John Kunz, where he put all the most important attributes in an overview. He collected the most important ones. And this is also a good read to kind of remember certain attributes that you can always or very often use at least. And this is where you would find the stopped attribute as well. So pretty helpful thing. So we basically do the same as we did for pop grains. And the best way to do this, of course, is first to deactivate all the points with a point wrangle, and we call this stop, let's say. And this is an integer. And in this case, we say stop 3. 1 would work as well, but to follow the rules from the help, this will deactivate rotation and movement. So stop set to 3. And if we run this now, we should see nothing. And you can see it still calculates, so it's pretty slow, but nothing happens, which is a good sign in our case. And from here, I have to take over for Houdini 19 because a small thing has changed since the last time I recorded this. So what we have to do now, of course, we want to activate those attributes really, because it's just setting stop to 0. And for this, like with all the other cases before, we have to, if we want to change it during the simulation, go into the Vellum solver, into the dive target. And here's where something has changed. And before we only had a force output, and in this case, we want to change an attribute on the geometry, which is neither a force nor a source. So now the question is, where do we actually now put our nodes in? And for some weird reason, it's source. So first of all, what kind of nodes can we use? As usual, we can use a pop wrangle because Vellum is point-based. We can also use a geometry wrangle, which is just a more advanced version of the pop wrangle. And then we can also use a geometry VOP. So if you prefer VOP, you can do it this way. But we will do it in our good old SOP solver way, because this way we can use all the nodes that we know from SOPs. But you know, my point is you can use all kinds of versions. The SOP solver, I'm actually not 100% sure if the wrangle wouldn't also work with force, but to be safe, always connect your stuff to the source output, because then it works. The reason for this, by the way, is that when you look at the Vellum, the way the Vellum solver is put together, it has to do with where this node is set and how it is connected. It's a bit strange, but just accept that if something doesn't work with a force input, it will probably work with a source input, even though it's neither force nor a source. Anyway, what do we want to do? In the SOP solver, when we go in, we can now change all the attributes on our head. For example, of course, with a group node. And what we want to do is either we put in an object here as a second input to define what parts we want to activate, but we could also just animate the group node directly, because all we want to use is some kind of region, maybe a bounding sphere, and maybe put this here and make it a bit bigger. And we can animate this here on the group node directly if we want. So let's start on frame 1 to with this position, and then maybe in 2 seconds it should move over here. Let's see if that worked. It did. And of course what we now have to do is we take a point wrangle and we choose the group we just created, and we kept it at group 1 because we're lazy. And all we have to do is, of course, we have to set the stopped attribute back to 0. So everything that is inside of our group will be activated. Make sure you look through the point wrangle so it actually does something. I'm not sure why it turns black, but just to make sure we can go outside and look at the whole thing from the outside, which is generally a good idea anyway, to be absolutely safe. And then we go back in just to change stuff, and let's see what happens. And remember, we turned off our weld constraint, so all our pieces should just fall down. And yes, it takes a little bit, but at some point it actually does something finally. So now that we have a couple of frames cached, let's have a look at this again, and this is how it looks like. A bit fast probably, so maybe we can slow this down by changing with Shift the keyframes, something like this. But overall it works. Okay, so this works now, which is great. But of course, it's a bit boring when it just falls down. So let's make this a bit more interesting. For example, by adding a little bit of wind. So whenever the pieces are activated, they should fly away. So of course, what we could use for this is the internal under forces wind function. But I'm not a big fan of that, because what's missing here is control over the noise. So I would actually turn this off. I would even turn off gravity for now, so that we have full control over the forces and recreate every force that we want ourselves. So for example, we could now go in and then here create a pop force, of course. And now, of course, this goes into the forces, not into the source, even though I'm not 100% sure, but I think it would still work. But let's be clean here. And now, of course, we can add a force. So this axis here, again, you can't see is X. So what I need is a negative number, so maybe -3, so that it moves to the right. So this is how it looks like. And you can see now, yeah, the pieces fly away. But you can also see it looks pretty boring, because they just, you know, fly away in one direction. And this is why I like to have this noise built in, because now we can add a little bit more variation and interesting chaos to this. So now it looks like this. And yeah, that's a lot more interesting. Maybe the whole thing happens a bit too fast, and I just realized I made a mistake. And that is in the group, actually, when we look at the behavior, the whole movement speeds up and then slows down, which of course is because the default curve here for X is an S curve. And I think it will look better when we linearize this, because then it keeps the same speed and the whole thing will start earlier and will not, you know, feel so fast once it hits. And another thing I want to change is actually we turned off our weld constraint. Now this means that all the pieces just fly around, but what we want to do is that you feel like they, you know, they resist a little bit the breaking up, as if it would be something like skin or something. So let's activate our weld constraint again, and we still have our breaking threshold turned to the default, which is 0.1. Let's see if that does anything. And the problem now is, while the pieces are activated, they don't move because the breaking threshold is simply too high. So our little noise there and the little wind that we created is simply not enough to break them apart. So let's first lower the breaking threshold to something much lower so that we can actually see if this works. Okay, so now it looks like this, which isn't too bad. You can see what I'm talking about. They kind of try to stay together before they break apart. So actually, let me increase that a little bit, maybe to 001. Maybe we can make the effect even stronger. Well, now unfortunately nothing happens again, so it is too high. So let's adjust this, maybe to 003, so 3 times stronger than we had it before. Now it looks like this, and I think, yeah, I like that. You can see the effect is even stronger, the, strength that keeps it together. And that is especially interesting because what we want to do next is we want to increase the amount of pieces, because it looks a bit boring. So to make it really shine, let's increase that maybe to 1000, yeah, something like that. And I think the resolution is good for this. Let's turn off the visualization and let's run this again. Now it looks like this, and yeah, and we still have some resistance. It feels like they're still fighting getting ripped off. We could even increase that. Maybe I do this. Let's maybe try 5 and see how this looks in a second. But before we look at the result, there's one last thing that is kind of obvious. And here we can see the normals are kind of broken. They're not actually broken. It's just that they're wrongly calculated because, of course, the edge fracture broke it up. And before it looked like this, and now it looks like this. But of course, there's a solution for that, and that is the Vellum post-process, because that is specifically made for this problem. And as soon as you run this, you can see it's fixed it already because the apply welds is turned on. And this means that the normals will be recalculated as if there would be no breakup or no fracturing. And now let's have a look with the slightly increased breaking threshold, how this looks like. So here we go. And I like this result even more than the last one because, that's the idea that some pieces even stay together because the strength is not high enough of our wind to break them apart. So let's finish this by just combining this with the actual normal head. And with a merge, we can just bring our original head in. And when it breaks apart, it currently looks like it's the same face. So let's change the color. Maybe see the underlying one is a bit darker. Of course, you can, adjust the shading to make it even look nicer, make it gold or whatever. But this is really just quickly for the viewport. And I think now, yeah, it looks pretty nice. So yeah, this is our peeling effect. And of course, feel free to play around with the settings to find your own solution. But for now, I hope this is helpful. So thanks very much and see you later. Cheers.